So again, we're going to find the internal forces, this time at the point C. So that's that little black dot there. And it's just to the right of the point of application of this moment here. Now remember, in terms of the external forces, it doesn't really matter where this moment is. But for the internal forces, it does matter. It's the same as when we're doing the internal forces, we redraw the UDL, or the line load, and we draw it on both sides, and we figure out the equivalent point load on one side and the other side to figure out the internal forces. It's similar with these little point loads. So it does for the external forces, if it's a free vector, it doesn't matter where it goes, it won't change it. When it comes to the internal forces, it does matter where it is, and so we'll just have to be aware of that as we're working through this. So first things first, I've drawn a free body diagram. I've drawn on the moment, so the moment's on there. What else do we need? It's in the right place though, not really. Let me just shift that across a little bit. Maybe about here. We're needing a force, so it's a rectangular line load, or a UDL, and so therefore the equivalent point load is going to be smack bang in the middle. And the magnitude of that point load is just the area under the UDL, so it's going to be 10 times 4, it's going to be 40 kilonewtons, the equivalent point load for that. So let's just put that on as well, 40 kilonewtons. And the first thing we need to do is to find the external reactions, so the reactions to this. So what have we got here? We've got a pin at this end, we've got a rocker at this end, and they've stuck the rocker at an angle. Now they've stuck that at an angle so you get a axial force basically, and so that's why they're doing that. And not an arrangement you would usually see on site. Can't think of one unless you're making a castle with a drawbridge or something like that. So let's just add on our reactions. So we're going to get FAY here. Let me just check what zoom I'm at here. And FAX. Now I'm just thinking about what direction to do this. I'm just going to draw on in the direction I think it's actually going to be in. So we're going to have a reaction here. It's going to have a component. So it's going to be, oh well, we could just draw it on here. So we've got some, it's in the middle, it's joined with a pin in the middle, so we'll draw it to the middle. Now that's 30 degrees, the surface, so this must be 60 degrees. Do your angles rules if you can't see why. And so we're going to have some load like that. And that we're going to call FB. And it's probably going to be easier for us if we split that up into its X and Y components. So we're going to have an FBX. Just going to get rid of this actually, because I'm just going to replace it with its X and Y components. Might not be a good idea. I'm just thinking ahead to what we're going to have to do here. So we might have to use this. So I'm just going to leave it on in a different color. I'm going to do that in green. Hopefully you can see that okay. FBX. And then I'll just stick on FBY as well. I'm just doing that because I might need, so if we end up with a single equation with both of these variables in it or something like that, I might have to refer back to the fact that it's an angle. What am I trying to say? Might have to write these in terms of that magnitude there. So just call this FB. Okay, but they're not all acting at the same time. Just these things are equivalent to each other. We better put on an angle if we're going to do it that way. This would be 30 degrees and this would be 60 degrees. Either one will do. We'll just do the 30-degree one. See whether we need that or not at the end of the day. What am I forgetting? So that's a pin connection. So we must have an X component as well. Oh, that's why I was doing all that. And so you can see this is going to have an X component in this direction, and so it's going to have to be balanced at the other end. So I would imagine that the reaction is going to be in this direction. So that's going to be FAX. Is that everything? I haven't put dimensions on, so I better just stick those on. Just for when we start doing our calcs. So it's just 222. Meters here, 2 meters there. Next, So let's try and figure out what these are now. So it's the usual thing. For equilibrium, we must have the sum of the x components is equal to 0, and therefore Fax must be equal to Fbx. Fax must be equal to Fbx. I've kind of jumped ahead there, I suppose, but you could probably start to do this now. You know, this is going this way, this is going that way, so the magnitudes must be equal to each other. You could do it just to show you that I'm not cheating. You could do it properly, in which you'd say Fax, so that's in the positive direction, take away Fbx, because it's going in the negative direction. We haven't shown that, so we should. Just call this, so y is always perpendicular to the beam. It's the y direction. X is always parallel to the beam, straight down the center usually. X is this way. And so, yeah, this one's in the negative direction, must add up to 0. So therefore, Fbx equals Fax is equal to Fbx. Now we might come back to that later, because we don't know what Fbx is. We don't know what any of these are at the moment, but I have a sticky feeling it'll come out in the wash. So we're going to probably be able to find out Fay and Fby. Those are going to add up to this, and then we're going to use all the moments. We'll be able to figure out one of those, substitute it back in, then we're going to get Fby, and then we should be able to use the angle, and we could probably just put a wee dotted line for Fbx down here just to show it. So we're going to have Fby, therefore we are going to be able to figure out, that's 30 degrees, we can use tan to figure out what Fbx is. So just thinking a bit ahead about how we can probably do this. Then we've got the sum of the y components is equal to 0. That means, so Fay, so it's in the positive direction, Fay plus Fby plus, not so much plus, so there we've got two of those components. Now we've got a negative components going in the negative direction, so minus, wrong colour, minus 40. Anything else? Nope. Equals 0. Therefore, Fay plus Fby is equal to 40 kilonewtons. Kilonewtons. Grand. Now, we've got our last weapon in our arsenal. It's the sum of the moments is equal to 0. And what will we take? Might be tidier. So what I'm going to do, so this is A side and this is B side. So I'm just thinking, we don't know this. So if possible, it would be nice to eliminate it from the moment. So it would be nice to take the moments at B. Then this force here has no lever arm. These components don't have any lever arm either. And so that would eliminate that. And then we're going to get a nice answer for Fay. Put that back in here, get Fby. Fby we've got. Then we can use trig to find Fbx. And then we can use this to find Fax. So let's go through that now. Maybe fast forward through this bit. So did all that, and so worked through moments about V. So using this point, figure out all the moments. That brought me Fay, because lots of them have no moment. So Fax is gone because it doesn't have a lever arm to B. Neither do any of these. And so could figure out Fay, took that, put it back in here, and that let me get Fby. this one over here. Then just use trigonometry to find out FBX. That's FBX down here, this one. So we've got FBX. And then I have taken FBX. We know it's equal to FAX, so that gave us FAX. So those are equal and opposite. So FAX is 11.9 in that direction. And then what have I done? So then we've checked the moments about A. So this is just a check to make sure it's okay. So I've just taken the moments around A and I'm just going to check that they do all balance out, and it does. And so you can always check that you've got the right answer just by using the other side. It should still be 0 if all these reactions are correct. You should get 0 moment at this end as well, and we did. So that's that done. So we've got all the reactions now. And so now we're going to split the beam at the question at the point they're asking about. So they're asking about C, which is just a little bit to the right of this, just a very small amount to the right of this. And so I'll do that now. I'll grab this and do a new free body diagram. I'm going to put on all the values we've got. I'll probably keep this as components. It's just easier that way rather than using the resultant for that reaction. And then we'll figure out what the internal forces are. So I've drawn my free body diagram with the beam split into 2 halves. As I mentioned before, you don't have to do this, so go to all the effort of redrawing all this, but you do have to be very careful about which side you're thinking of at any one time. If you just try and do it all from this diagram, just draw a line through here, you just have to be imagining this. Make sure you're imagining this, otherwise it's very easy to get confused about which direction's positive and negative. So far I've been using normal sign conventions, just relative to the x and y axes for the forces, and anti-clockwise positive, clockwise negative for the moments. It's just at this point you come in, we're finding these internal forces, we split it to reveal them, and when we draw them on so it produce positives and negatives for those internal forces as per these diagrams. Okay, so we draw them on as if they're positive. That'll mean that the correct sign comes out in the wash. And so we're on the right-hand side of this one. In fact, just looking at it might be, almost certainly, will be easier to do it on the right-hand side part first, but we'll just draw them onto both, and I might just use the right-hand side one for the calc, and I'll use the left-hand side one for the check. And so we've got a normal force at C, I think this wasn't it? It is C, correct. So we've got a normal force at C, so we're on the right-hand side, so positive would be this direction. You can probably guess already that it's going to come out negative. Why? Because it's compression. So you've got to, let me go back to this one. We've got forces pushing in from each side, so this must be in compression. So the internal force should be negative. The internal axial force, the internal normal force should be negative because it's this situation. But by drawing this on in the positive direction, that will come out, it'll end up being negative. And so that's why we're doing that. And similarly, we want to draw in the moment here. So this is MC, and we're just drawing it on to get a positive bending moment, sagging. And so it's on there, we're on the right-hand side of that part, so it needs to go that way. So that's MC, and we'll probably have a shear. So for positive shear, it should be downwards on the right-hand side. And so this would be VC that way. Whereas on the other side, then a positive moment is going to be this way. So that's going to be MC as well, because they're all identical. These have to be the same, because it's all the internal forces at the same place. This one, NC, so it would be looking at positive, but we're on the left-hand side of this part now, so it should be going that way. So it's going like so. That would be NC. And the shear for positive should be going up at this side. So it should be like that. I might draw it with the nose at the point of application. And this will be VC. Okay, so this is the only place where you use these weird sign conventions. It's just when you've split this apart and you're trying to figure out which way to draw these. you use this and you look at this and think, right, I'm on the left hand side of this, so I need to draw on in the positive direction for shear. And so left hand side, that one's up, this one, the right hand side would be down. That's why I've drawn it down on this side. Okay, so then I'll ditch those again. I should maybe just leave them on just to remind you that that's what we're doing. I'll just leave them there. Now what am I going to do? So now I'm going to use one side or the other. So you're switching back to your normal sign conventions now. Just using normal sign conventions. And I'll probably calculate it with this side and check it with this side, I reckon. Let's give that a go. Okay, just being careful here. And so I'm on this side, I'm using this one. So we're using normal sign conventions. This is going in the negative direction compared to our axis. So that's negative NC. Lucky I stopped. NC. And similarly here, NC. And this is also negative 11.9 kilonewtons. And so we are going to end up with negative NC as, take that over to the other side, it becomes positive. So NC is equal to negative 11.96 kilonewtons. So we know internal shear force, internal axial force equals negative 11.96 kilonewtons, and I'll just put in brackets. That means it's in compression. If I hadn't put it in brackets, I'd have to take away the negative sign. So you'd have to say equals 11.96 kilonewtons compression. Do you know what I mean? So by putting it in brackets, you're just saying this is compression because it's minus. But if I take the brackets away, I'd have to take off that negative because you're saying it's 11.96 kilonewtons compression. We probably wouldn't. That's our final answer. I don't think we're going to use that. I'll use it to check it. But anyway, 11.9 kilonewtons in compression. And then I've also done Fy, so I'm being similarly careful. VC positive. And then we've also got the reaction is positive. And so then we take this across to the other side. It's negative. So negative 20.62 kilonewtons. And so internal shear. It's getting late in the day, I can't write anymore. Internal shear equals negative 20.62 kilonewtons. And we don't have it's a final answer, so negative 20.6 kilonewtons. We don't have an equivalent, an axial force could be compression or tension. We don't have an equivalent for shear. It's just negative or positive. So in this case, it's going to be negative 20.6 kilonewtons. What does that mean? It means that this force was the other way, it should be the other way around. And that would give us, should be downwards, that would give us this one. That's negative shear. Okay, that's the negative shear. So it's worked out fine just because we drew it on the right way to start with. The last one's the moment. Sum of m is equal to 0. Just need to pull it down so I can see what I'm doing. Again, I'm using this side. So we're going to get, so that MC is clockwise, so it's negative MC. Well, what am I doing this about? Let's do it about B. It's going to eliminate more forces. Whatever, doesn't really matter, I don't think. So that's negative MC. Then we've got, if we're doing it about B, we've got VC going this way, so that's tending to rotate this clockwise, so it's also negative, and it's VC sine 2. We know VC, we do. Should be okay, I think. I'm on the right track. Negative VC times 2, and then all the stuff at the other end just disappears because it's got no lever arm. This NC also doesn't have a lever arm to that point, so it disappears too. I'm talking about this one here. So its line of action goes through B, so it's got no moment, equals 0. We've already figured out VC, so negative MC negative 2 times, let me just think about this for a second. So this is negative, yeah, that's cool. So I thought about this using this one, VC going in this direction. This is saying it's the negative of that, and so I'd have to actually put that negative in there. So that's negative 20.6. If that's confusing you, what you could think about on the other side is it's actually like this. So that VC is negative 20.6. We've got a negative answer for that. So VC is actually down the way like so. That's where it should really be. And that would make this whole thing positive because it's now turning it anti-clockwise around B. So at the end of the day, the whole thing should end up positive. And that's what's going to happen. So minus MC plus 41.2 goes 0. So therefore MC negative MC is equal to, just because I know the answer, so negative 41.2. It's all very useful knowing the answer. I don't mean I know the answer because I've done this before. I just mean I know the answer because I know that for a beam like this, the bending moment is going to look something like this. Actually, no, it's not. It's going to look something like that, straight lines. And we're going to get to that just shortly. It's called the bending moment diagram. So something you'll do next actually helps you with these problems as well. Anyway, back to this. So I know it's going to be positive at the end of the day, so it's going to be 41.2 because those negatives cancel out. So 41.2 kilonewton meters. I think we're done. So bending moment equals 41.2 kilonewton meters, and that's sagging. And then all we have to do now is underline those and then check the answer using the other side. So I'll just do that in grey, and that'll be us done. So I'll just finish that off. I'll fast forward through that bit and pause for a little bit at the end just so you can see the check if you need to. Okay, so nearly caught me out again. So I've drawn on VC to be positive to give us the right shear from here. When it came through, it's negative. So actually it's the other way up. It's the other way up. Can deal with that by just putting negative in here when you see the VC, or what you can do is just keep in your mind what it really is. So that was negative what I'd drawn, so it's actually the other way, which when it comes out in the wash, so it's really going up this way. Let me just do it in a different colour. It's really going up this way, which overall will give me a positive moment. Okay, and you're going to see here when I do a negative times a negative, I'm going to get a positive moment there. So that's going to work out. So it worked out in the end. It's a little bit different. Must be a rounding error in there somewhere, but it's close enough that I'm happy I've got the right answer. Okay, that's that one done. Okay, now I think you're onto the tutorial sheet after this.